Okay, let's make it happen, folks. The challenge is in front of us. Let us add up the area of an infinite number of rectangles. This is our formula. Let's write it again on the top. We're going to whoop. Nope, we got to go back. Go example 5. We say that the integral from a to b of f of x dx, that represents the area bounded underneath the curve in the x-axis between a and b. That's going to be equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. We said delta x is b minus a over n, and x sub I is a plus I times b minus a over n. I know it's confusing. I know that some of that stuff, you're like, I don't even know what it means. But we laid out what x sub I is, and we laid out delta x. The x sub I piece is a little bit confusing. We're going to make sense of the rest today. So we want to consider the area beneath the curve x cubed from 0 to 3. We want to find the exact area. So I don't want to find the width of 3 rectangles. I want to find the width of n rectangles. Anybody know what that is? So 3 over n is the width of n rectangles. If I would like to find the spot at which we evaluate the sum, those are my x sub I values. So if you look over here on the board, again, you know, we go over 1 width, 2 width, 3 widths, 4 widths, 5 widths from A. So we start with A. What is A in this problem? We add on to it I widths, and the width is 3 over n. And we get 3I over n. Notice that the actual width and the x sub I values are very, very similar, aren't they? That's not always the case. If this was, say, 2, then you would have a 2 plus 3I over n. Now, why does that make it more complicated? Because when you plug that into the actual function, you would cube it, and that would, you know, just the algebra would be a little bit messy, right? So we'll do an example exactly like that tomorrow. But today, if you do get far enough in your worksheet, that's what you would have to do, is do the plus 2, okay? So we got 3I over n. Let's express the area as a definite integral and as a limit of a Riemann sum. So the integral says the area bounded from 0 to 3. What's my function? X cubed dx. That's equal to, and then this is what we're trying to solve. Limit as n goes to infinity of the sum from I equals what? 1 to n. We write that every time. Then we have f of x sub I. What's x sub I? 3i over n. So what do we do with the 3i over n? We plug it into the function, x to the third. So we have 3i over n cubed. I stands for this. We start with the first rectangle, then the second, then the third, then the fourth, then the fifth. And so as you look at this up here, we go over to the first one, then the second, then the third, then the fourth, then the fifth. We just keep on going. And so we start with 1. So I is the rectangle number. We start with the first rectangle, and we go to number infinity, which is not a number. And so multiply by the width. Remember, this delta x is the width, 3 over n. We'll multiply that out. I have the limit as n goes to infinity of the sum from I equals 1 to n. 3i cubed. 27i cubed times 3. 81i cubed. Let's do the bottom. Now you have n cubed times n. N to the fourth. So we have it, yes. Yes. I have a nice expression right here. But what I want is I only want n. Look, I got to let n go to infinity. But I've got these i's in here. I want to get rid of the i's. So I've got the limit as n goes to infinity of, we're going to take out the 81 over n to the fourth, and we're going to leave the sum from I equals 1 to n of I cubed. All right, so substitute a known sum. We have it right up there on the board. The sum of the first cubes, we have the limit as n goes to infinity of 81 over n to the fourth. And then, as I said, the sum of the first cubes is n squared times n plus 1 squared over 4. And I'll prove whichever one you guys want me to tomorrow, okay? Whatever you decide you want me to prove tomorrow, we'll do it. What's that? Oh, yeah, I is 64, yes. That'll be impressive. Well, that's not a big deal. I mean, we could do that. We know infinite limits. It sounds ridiculous, but we're really smart. So I've got 81 n squared times n squared 2n 1. Everyone okay with that expression? Oh, 8 natural log squared. All right, I like it. All right, so we've got the limit as n goes to infinity of, oh yeah, thank you, 4 into the fourth in the denominator. So I've got 81 n to the fourth, 162 n cubed, 81 n squared, all over 4 n to the fourth. I'll do better 4 that time. What now? Take out n to the fourth. Very good. So we got the limit as n goes infinity. Now, it used to be like, well, how do you do infinite limits? I mean, my gosh. You just do it. All right? We tested on it. You guys know how to do this stuff. So we take out n to the fourth, we get 81, 162 over n, 81 over n squared, all over 4 n to the fourth. What happens? N to the fourth is gone. Fractions cancel y. Yeah, 162 over a really big number is going to be 0. And so those are both going to be 0. We end up with 81 over 4, which is, as a decimal, 20.25. Now, I know that you're a little bit skeptical of the result. You're like, you know, invalid floating point operation? What the heck? I've never gotten that error before. Wow, we broke. Unbelievable. Let's try to quit this application. Close window. Will you go away? No, I just floated it to a wrong point. I don't know. Okay, we'll have to fix that. So go to your calculator, type in the function. Go f of x is x to the third. Okay, so after you do that, go second. Yeah, no. So y equals go x to the third, and then go second calculate number 7. Jeez, whatever. Okay, and then you pick number 7. You'll draw the curve, and you pick the lower limit, which is 0. The upper limit is, and you should get 20.25, exactly what we have. So today, that's how you check your answer. So I'm going to give you the worksheet. You're going to try a little bit now, and after we get back from lunch, you get the first problem. Then we're going to do the next problem, and we'll be good to go. So let me pause this. Okay, let's check it out. We pick up with example 6. Consider the area beneath this curve from 0 to 4. I always start with delta x and x sub I. I always start there. What is delta x in this problem? Very good, 4 over n. X sub I, 4i over n. You must do this part. I will expect to see this part on the test. Integral 0 to 4 of 2x minus 1/2 x squared dx is equal to, I'm expressing the definite integral, which we will learn to do on Wednesday. I'm expressing that as an infinite limit. You need to express your work as I am doing. Yes. So it always starts out like that. What do I then do? Plug what in? Plug in x sub I for x. If you notice here, I have 2 spots, don't I? So I'm going to be careful there. I've got 2x, I'm sorry, 2 times 4i over n minus 1/2 times 4i over n squared. And that is all being multiplied by 4 over n. So sometimes people won't put that delta x through to both pieces. We got to clean that up. Limit as n goes to infinity of, what's my first term? 8i over n minus 4i squared, 16i squared, then divide by 2 would be 8i squared over n squared times 4 over n. What should I do now? Let's first distribute, and then we'll do that. Limit as n goes to infinity, sum I equals 1 to n, 32i over n squared minus 32i squared over n cubed. Notice that I is 1 degree lower than the n, right? It should always be that way. Your power for n should be 1 degree higher than whatever I is in the numerator. Finally, I'm going to write it like this. The limit as n goes to infinity of 32 over n squared times the sum from I equals 1 to n of I. And I'll do my second one. Minus the 32 over n cubed times the sum from I equals 1 to n of I squared. So we can break the binomial up into 2 sums. Yes. So what do we put in the place of this? Yeah. Let's say that this wasn't an I. Let's say it was a constant. Let's say it looked like this, folks. Let's say you had a 2i over n. Then it would be 2, whoops. Let's say you had a 2 over n here. You remove it, you have 2 over n times the sum of I equals 1 to n of 1. our rule up there says if you have a constant, you replace it with the constant times n. What's 1 times n? So you would get rid of this, you have times n. You can see you just end up with 2. Sure, if you would have left the 2 there and had a 1 over n, then you have 2n. It's going to end up the same regardless, okay? So I think for number 4, you have a constant, so you're going to treat it like that. So it looks like I now have the limit as n goes to infinity of 32 over n squared times what? What do I put in its place? Good. Minus 32 over n cubed times sweet. Or the limit as n goes to infinity. What's the top going to look like for the first part? 32n squared plus 32n over 2n squared. Minus, I know that this gets a little bit trickier, but we've done it a couple times. Yeah, 2n times n is 2n squared times n is 2n to the third times 32 is 64 n cubed. When I take this binomial, I multiply it. What do I get in the middle? 1n and 2n make 3n squared, so 96 n squared. Then 1 times n is n, 32n. Okay, find the limit. Fortunately, this isn't a big deal for us. We know how to do this. We practice this many times. N goes to infinity. What do we take out of the top? N squared. We got 32 plus 32 over n over 2n squared. And then out of the second one, I take n cubed. See, 64 over 6 is 32 over 3, and 16 is 48 over 3. So I get 16 over 3, which is 5.3 repeating. Ooh. Okay. I take out my handy dandy calculator. Yeah, hopefully we do not get another invalid floating point error. Awesome. So got y equals, what's our function? I'm going to check my answer by doing second calculate, number 7. Going from 0 to 4. I mean, it is pretty impressive, isn't it? If you think about what you just did. After we got through the habit of drawing 4, 8, 12, 16 rectangles. Well, I promise on Wednesday I'm going to show you a way of doing it that's even quicker. In some ways, I'm quicker than the calculator, yes. Okay. But, no, it's good stuff. So you have your worksheet to do. Just note those slight changes. If it doesn't start at 1, or if it doesn't start at 0, you got to change that. So we'll go over the last example tomorrow. There's only 3 days to fully kind of get this through your system. So